An important topic in matrices is the idea of row reduction. Before getting into what row reduction is, we must first understand what matrices are. Matrices are nothing more than a convention of storing an array of information in a compact, organized, and sometimes more visually appealing way. For example, this matrix can be used to represent a system of equations like so. Notice that the same numbers appear, except their appropriate significance or context is visible. In this case, we can see that each number represents the coefficient of a variable or a constant in a system of equations. But how can we define a reference matrix and its different components? Every matrix has rows, the horizontal lines of entries, and columns, the vertical lines of entries. Together, they define the dimensions of a matrix, which is the number of rows by the number of columns. Note that they are not multiplied. We just say rows by columns. Going back to our other matrix, we can see that the first column represents the x coefficients, the second column represents the y coefficients, the third column represents the z coefficients, and the fourth column represents the constants the sum of the terms are equal to. Each row represents a separate equation. Writing this out gets us the following system of equations. Rearranging the order of equations does not change the value of each variable, nor does it change what the system of equations represents. In a matrix, this is the exact same as just swapping any two rows. This is one of the three elementary row operations in a process called Gaussian-Jordan elimination. To say that we swapped row 1 and row 3, we write R1 or row 1 swapped with R3 or row 3. More generally, this is Rn or row n swapped with Rm or row m. In algebra, you are taught that you're allowed to multiply both sides of an equation by a number. This is an important tool for elimination or for isolating a variable. Here, we can multiply both sides of equation 3 by 4. In our matrix, this corresponds to multiplying the whole row by 4, which is our second elementary row operation, multiplying a whole row by a non-zero constant. To write this step out, we simply write 4 times row 3, store that into row 3. More generally, we would write c times row n, store that into row n, where c is some constant that is non-zero. Now, if you were given this system of equations, what would likely be your first step? For most, they would notice that these 4x's can be eliminated by subtracting equation 2 and 3. To successfully subtract these equations, we must ensure only corresponding variable coefficients get subtracted. Subtracting 4x minus 4x equals 0x, 5y minus 8y equals negative 3y, 6z minus 12z equals negative 6z, and 5 minus 36 equals negative 31. Normally, we'd call this new equation we get something like equation 4. But now, what would that mean for our matrix? We can't simply add another row, since that only makes things more complicated and messy. There are two options. We can replace row 3, equation 3, with this row of numbers, or replace row 2, or equation 2, with this row. Why not row 1? Notice here that we used equations 2 and 3. Nowhere in this step do we use equation 1 at all, meaning it has still some unused information. Thus, we must leave it be. Imagine I'm thinking of a number. It's a perfect square, it's even, and it's less than 12. We can use hint 2 and 3 to determine this number could be 2, 4, 6, 8, 10, or any negative even number. If we replaced hint 1 with this, we'd get stuck. There's no more information that can help us solve this. But by replacing either hint 2 or 3, we can then use hint 1 to determine the number must be 4. This is our third and final elementary row operation, adding or subtracting multiples of two rows. We're actually very familiar with this process. For this given system of equations, we can eliminate the x terms by finding a multiple of 3 and 2, 6, then multiply each by the appropriate number to get said multiple. 3 times 2 is 6, and 2 times 3 is 6. We then subtract both equations to cancel the two 6's. In our matrix, this is equivalent to 2 times row 1 minus 3 times row 2. Store that into row 2. So our three elementary row operations are swapping two rows, multiplying a row by a non-zero constant, and adding and subtracting two rows. Given this system of equations, how could we solve it using row reduction? Well, we'd first have to record the system as a matrix, which we can easily do by just taking the coefficients and arranging them like so, aligning x, y, and z coefficients. It is common to see a line drawn before the last column. This makes the matrix an augmented matrix, a matrix that we have augmented or added something to. Here, it's usually to discern what is a constant and what is a variable coefficient. In our equation, we're going to want to end up with a system of equations where we just have x, y, and z equal to some number. If you write this with the other variables visible, these equations look like this. So our matrix must end up looking like this. This inner 3x3 matrix is called an identity matrix. An identity matrix is any matrix with equal rows and equal columns, also known as a square matrix, that has a diagonal from the top left to the bottom right with ones, and everything else is zero. The best method to get this involves finding the 1 in a column, then the zeros, then moving on to the next column and repeating. Find 1, then zeros, move on, repeat. If we want our matrix to look like this matrix below, the element in row 1, column 1 must be 1. We can see that it already is 1, so we can move on to row 2, column 1. We want this element to be 0. Using our elementary row operations, how can we make 0 in row 2 with these numbers from the first column? We can just use 1 minus 1 to get 0. These 1's came from row 1 and 2, so writing this step out would be row 1 minus row 2. And we're going to store this result in row 2, since that's where we want our 0 to be. We have to apply this operation to each whole row, so we'll bring them down and compute their difference. Subtracting corresponding terms, 1 minus 1 equals 0, 1 minus negative 1 equals 2, 1 minus 2 equals negative 1, negative 4 minus negative 13 equals 9. Then we'll place this resulting row into row 2 and equation 2. Our system of equations will be displayed normally on the right side, so you can compare what each process does. We've got a 0 in row 2, column 1, so we can move on to row 3, column 1. Using the numbers in that column, we want it to become 0 as well. Here, we could do 2 times 1 minus 2 to get 2 minus 2, which is in fact 0. The 1 is from row 1, and the 2 is from row 3. We will replace row 3 since we want the 0 there. Writing our two rows together, and after multiplying the first row by 2, their difference is the row 0, 1, 5, negative 23. Placing this row into our matrix and equations completes the first column. We can now go on to row 2, column 2, since we want to start by getting this to be 1. Notice that the elements above and below 2 are both 1, so we may be able to use either of them to swap with row 2 and get a 1 in that entry. Let's try swapping row 1 and 2. This creates a problem. We now lose the 1 that was originally in row 1, column 1, and the 0 that was in row 2, column 1. So we should probably not swap row 1 and row 2. Always make sure you aren't losing any progress before performing a row operation. How about swapping row 2 and 3? This is okay because our column 1 stays as 1, 0, 0, which is what we want. Now we'll move on to row 1, column 2, which should be a 0. Using the numbers in the same column, we can get 0 by subtracting 1 and 1, the first being from row 1 and the second being from row 2. Their difference is the row 1, 0, negative 4, 19, which we'll put in row 1 since that's where we want our 0 to be. On row 3, column 2, we want a 0. Note that we can't simply swap row 1 and 3 to get 0, since we'll end up throwing more entries out of place like the blue 1. We can get 0 by multiplying 1 from row 2 by 2, then subtracting 2 from row 3. We'll put this in row 3 since that's where we want our 0. Multiply row 2 by 2 gets us 0, 2, 10, negative 46. Subtracting row 3 then results in the row 0, 0, 11, negative 55. We are now done column 2 and can begin column 3. We want row 3, column 3 to become 1. Notice that 11 and negative 55 are both multiples of 11, so we can divide row 3 by 11, which will just so happen to give us 1. In the case where the entries weren't integer multiples, you may have to divide and get fractional values just to get a single 1 in that entry. Dividing row 3 by 11 gets us 0, 0, 1, negative 5, which will store back into row 3 so we can get that 1 in row 3, column 3. In row 2, column 3, we need a 0. We can get a 0 by taking 5 minus 5 times 1, with 5 being from row 2 and 1 being from row 3. Multiplying row 3 by 5, then subtracting gets us the row 0, 1, 0, 2, which we'll place in row 2. Finally, row 1, column 3 needs a 0, which we can get by adding it to 4 times 1 from row 3. Multiplying row 3 by 4, then adding row 1, returns the row 1, 0, 0, negative 1, which will be stored in row 1 for the 0 in column 3. And just like that, we have our identity matrix and have finished the row reduction. The solutions to the system are the constants left over, negative 1, 2, negative 5. This is because if we rewrite the system of equations on the right so that the 0 coefficients are invisible, we get 1x equals negative 1, 1y equals 2, and 1z equals negative 5. Neat, right? Let's do one more, except with only matrix visuals. We can convert this system of equations into a matrix by simply taking the constants and the variable coefficients. Starting with row 1, column 1, we want it to be 1. We can easily do this by dividing row 1 by 2 and storing it into row 1. Row 2, column 1 needs to be a 0. We can use 8 from row 2 and negative 4 from row 3 to create 0 by doing 8 plus 2 times negative 4 to get 8 minus 8, which equals 0. Doing the multiplication by 2, then adding row 2 and 3 gets us the row 0, 0, 0, negative 21. We'll put this into row 2, since that's where we want the 0 to be. Wait a minute. Let's have a closer look at that row 2. If we put this into an equation, we get 0x plus 0y plus 0z equals negative 21, which simplifies to 0 equals negative 21. That's incorrect, meaning there must be no solution to the system of equations. This is called an inconsistent system. And we can end the question here.